Welcome to my speed run of probability. I'm going to try and do this in 30 minutes-ish, mainly because I have to go to bed. But also because I think that we can totally do this speed run of probability spelled out in one sitting. Here are my attempts of some drawings. If you take a probability course, you're probably going to be hearing about coins and cards and dice for a really long time. But yeah, so that gets annoying. And so hopefully you won't have to deal with all that if you can just get it all in 30 minutes. And these are the topics that I want to cover. I'm going to go pretty quickly through this first half and spend most of the time in this second half with some bonus content at the end, because I think 1, 2, and 3 can be done. I mean, any probability textbook is going to go over like the exact same things here. And so I think those are less important to cover in this video, but it's the basics and the fundamentals. So gotta go over it in some sense. All right. So let's start off by building out the core of probability with number 1, counting. So if you've never taken a real mathematical look at probability, then, I mean, you still certainly have some intuition of what probability means, right? So if you just roll a 6-sided die, what is the probability that you roll a 1? And you, no matter who you are, you probably know that the answer to that is 1/6. But let's formalize why it is 1/6 and then build up from there. So we had 1/6, but where does that come from? That comes from the probability of what we said, rolling a 1. I think that's what I said. It is the sort of total possibilities, which you give that symbol, over the total events that make that happen. So that's confusing, but what really should be is like, it's just a fraction, right? And so we can, not ignoring all the math, we can just run an experiment. And so we're going to flip a coin or roll a die a lot of times, and then just record how many times a 1 comes up versus the total number of trials, right? And so we just record that, and then it becomes a fraction. And then that fraction is actually this fraction. And so what these two things are, so this represents an event. And there's a couple of sort of vocabulary words you have to get used to when starting out in probability. There are events, there are outcomes, and there are experiments. So let's go quickly over this, and then we're going to start the speed run. So an experiment is what we were doing, is rolling a die. So all of these things are basically translating real life experiences and trying to translate them and formalize them to be used to do math. So an experiment is something like rolling a dice. And an outcome of that experiment is a 1. Or maybe a 2, or maybe a 3, or whatever. And then an event is a collection of outcomes. So it could be rolling an even number. And so there are a few outcomes that match this event, and therefore it's kind of a collection. So it's like a 2, a 4, a 6, right? All of those outcomes match the event. So you can kind of think of it in this direction. So those are 3 important vocabulary words that you should pause the video and actually understand, because it is actually surprisingly confusing at the start, and just gotta like make sure you kind of get that. So once we have those 3 vocabulary words, and maybe set theory, and so this notation makes more sense, but realistically you don't need to know too much about that. You just need to know the probability of the event equals sorry, one more sample space. This is all the possible outcomes. So in the case of the dice, is 1, 2, 3, 4, 5, 6. Those are all of the possible outcomes of the experiment. So how many possible outcomes do we have is 6. And then in that original case, the event was also the same as an outcome, which may be kind of confusing, but the event is, do we roll a 1? And so in that case, how many outcomes fall under that event is just 1. But if we were to do probability of a different event, and then let's say that event, we're just using a letter here because that's typical notation and you'll get used to that. So we see probably a different event, and that event in plain English is we get an even number. So same thing, there's only 6 possible outcomes of rolling a die, and that is the sample space, and which has this nice symbol. And then how many outcomes fall under that event? Well, we wrote down 3 different numbers, so it's 3 or 1/2. Great. So that is the sort of core understanding of probability. A probability is, in a general sense, just a number. The probability of whatever happening is a number in between 0 and 1. As you've heard throughout your life, 30% chance of rain, whatever it is. It's a number between 0 and 1. So now that we know what a probability is, it's time to start counting, and we're starting to make our way up here. So it's time to start counting so that we can actually calculate more probabilities of more complex experiments and events. So basically you could ask with, now it's time for the cards, is like, what is the probability of getting dealt 3 queens in a row? And so right now we're in the same land where we have an event. So we have this event A that corresponds to, in English, 3 queens in a row. So probably that, and we know it's a fraction, it's between 0 and 1. So we have to count these 2 things. And so there is surprisingly a lot of strategy in counting. Counting is probably arguably the hardest part of probability, and just doing the math behind basic probability. That's at least what I struggle with. So I suggest getting more practice than this, but we're just going, it's a speed run. So here we go. There's a couple of strategies. When you hear and, you think multiply. And when you hear or, you think about adding. Obviously there are exceptions to this, but that is sort of a useful thing that I keep in mind. So with that in mind, we want to come with the outcome of 3. We want to end up with 3 queens in a row. And so first off, okay, let's see. So the first queen, the probability of picking, that is, there are 4 queens in a deck. So the probability of picking one queen is 4 out of 52. And then we see the word and in a sense here, because we want the first queen and we want a second queen. So we know the next card is 3 over 51. And now you start to see a pattern here, and the next one is 2 over 50. Great, and so that fits our format here. I'm not going to do that math, and I'm pretty sure that is correct. So that is an example of a more complex counting where you're trying to determine the probability of some event taking place. Okay. So now, all right, this is a speed run. Now, let's see, we're going to move on to number 2 of conditional probability. So before we had the probability of an event taking place, and now we want the probability of an event taking place given and another event has taken place. So this symbol means given. It looks weird, but you definitely get used to it. So what is, let's see, a question. What is the probability of, okay, so our experiment that we're going to do is roll 2 dice, or die. And then we're going to keep track of the sum. Going to keep track of the sum, and the sum, you want it, so first of all, you want to know what are all the total possibilities of that sum. And it turns out, so we can have a 1 and a 1, and then that goes all the way up to a 6 and a 6. So it turns out to be a 2, can be 3, and then all the way to 12. And so if my first roll is a 6, that changes what the total sum can be, right? So B is the first roll, and I'm just going to tell you that that equals a 6. So that means that we are now stepping into the world where that sum has to be greater than 6, right? Because the next roll is going to be a 1 plus. So the total sum has to be something from 7 to 12. So the probability of A, and let's say the probability A is the event that the sum is greater than 6. Well, every possible option from now on has to be, the sum has to be greater than 6. So the probability of A given B equals 1. And so how you calculate that in a more reliable way is with this formula. So this means and, like we said before, and typically means multiply. So you might want to think about this, but be a little bit careful with that. And you just more want to think about the total possible options where they both take place. So all of the outcomes where A and B, yeah, great. Okay, that is conditional probability. And let's say you have two events. You have two events, but let's do different people here. Two events, but D is just completely unrelated to C. Like, the probability that I pass my final tomorrow given my friend back at home ate cereal for breakfast. Right? Those are completely unrelated. So why should D taking place update our sort of understanding of C and the probability of C given D? Well, it doesn't have to. So the probability is still equal to C. My friend eating cereal did not change anything for us. And so this relationship is called independence. C is independent of D. The D taking place does not affect C. And so that sort of opens up our world in a few places. And one of them is that we can now do this, I was saying before. There you can now do that. You can now do the Bayes rule, but you know what? Okay, so here's a couple of things that you should go study on your own. Bayes rule, super important. Law of total probability. And with that, we are going to get the heck out of the first half and get into the fun stuff of the second half. Okay, so random variables. So this is where things take a step up, in my opinion. So before, we were talking about events. And then an event was kind of just a collection of outcomes. And events had a probability. And that's pretty cool. But what if you want to collect more information about an experiment? So we had this dice roll, and with the dice roll, we could get a 1, 2, 3, 4, 5, or 6. That was the outcome. And then the probability was all the same, right? It was obviously all 1/6. But when we did the sum, it was 2, 3, 4, 5, 6, 7, The probability was not constant. Maybe think about why. Well, the reason why is because there's more numbers that add up to 7. It's like 4, 3, 2, 5, 6, 1, right? So the probability of this is 1 out of 36, and we could calculate that with our old strategies, right? Probability of A, where A means the sum is 2, which would mean there are 36 possible ways to roll the dice. And then how many outcomes satisfy our event where the sum is 2, well, it's only just 1 and 1 of that roll, of those rolls. So it's 1 out of 36. And you could calculate the same for 3. It's like there's 2 out of 36 because you get a 2 and a 1 and a 1 and a 2. Okay, great. So we can go and calculate all of these and make sure you understand that this probability is going to be 1, or all of these added up should be 1, but that's sort of unrelated. Okay, so you have this more interesting experiment, and we want to just sort of collect this information in a more formal way. And the way to do that is what's called a random variable. And you do it with like a big capital letter. And it's also like, it's the same way you're defining an event with some regular language. You're defining a random variable with with regular English language. Like, so x equals the sum of 2 dice rolls. All right. And so this might feel super similar, but x equals 2, this is just an event. This is nothing new from what we've already talked about. That is just an event. X equals 3 is an event, and we just calculated the probabilities for both of those. Where it can get a little bit more complicated is now, since this is a variable, you can say, what is the probability that x is less than or equal to 3? That is still an event and something that we can totally calculate. It'd be the probability that x equals 2 plus the probability that x equals 3, because it can be less than or equal to. Great. So you can have like those inequality things, and those are still events. And so we can have x equals to a constant, x equals da-da-da-da-da. But now let's step it up another level, and let's say, well, what if x is equal to, we can put the probability around here and know that this is a probability of an event. So what is the probability of x when you set it to a variable? Well, it looks kind of complicated and it looks kind of weird, but I mean, just kind of think of a regular function. That's kind of what I think about it as, is like if you had x equal, just oopsie daisy, the line x equals 2, like that is a line where x varies and stays at 2. Shit. That is y equals 2. Here is x equals 2. Right? So here, this is like, you can think about it as varying. And because of that, this represents what's called the probability mass function. And it looks a little weird with, these are called discrete. This is a discrete random variable, and I'll explain that in a second. It looks a little weird, the function, if you've never seen like a piecewise function, but realistically, this just captures this entire table in one function, and you can literally just kind of copy. So what's the probability that x equals 2? It was 1 over 36. And then what's the probability that x equals 3? And there's probably more that have the same probability, but it's 2 out of 36. And then you would go down for all of the things that x can possibly equal. Right, x can't equal -4, so that's not necessarily included in the probability mass function. But that is a way to just incorporate all of this data in one go. And that's what probability scientists and mathematicians want. They don't want to write out all that shit every time. They want to just have a PMF explain it all in one go. And so discrete means that it can only take on a certain defined amount of values. So we had basically from every integer from 2 to 12. So we kind of understand discrete random variables now. Discrete random variable, it just means that you have this function where you have a random variable and it equals something that's kind of changing. Like we're going to go up and see what happens and go down and see what happens. Y could be 1, Y could be 2, Y could be 3. We're just going to see what happens, and then we're going to make note of all the probabilities that it has, and then when we don't have probability, it just equals 0. So then that ends up kind of looking like this. It's like a piecewise function, something like that. Yeah. Great. Okay, so that's a discrete random variable. Now let's talk about a continuous random variable. So, what's an example of that? Well, let's see. It could be if you are spinning a dial or like a twister board thing, and you gotta you're gonna spin the dial, and then you want to see the likelihood that it lands exactly in this centimeter or exact atom. It lands right here. But if you think about it, if you go so small, such a small distance that it goes around and around, it lands at, that probability is actually in continuous land, probability that it equals 0.1432 equals 0. So in continuous land, probabilities are in ranges. So what would be easier to ask is like, what's the probability that it lands in this quarter? And I mean, if the spinner was equally likely to land in every spot, then that would be 1/4. Or if you have a number line, all right, let's formalize this a little more. So we have a number line from 0 to 10, and x equals, if you were like I don't know, flying this way, and then you're gonna land in you're gonna land in like, okay, you know those competitions with the dogs, and then they run, and then they jump, and they land in the pool, like they try to jump the farthest. Let's talk about that. So we have like okay, let's say 5, 7.5. Okay. So we're gonna, x equals the distance jumped by the dog. Great. And in this scenario, the dog is equally likely to jump to any location, which is not true, but it's good for this example. So that is our random variable, and it is continuous because it can take on any value in this range of 0 to 10. It can be 0.144445 with a million decimal points. It can be any distance in the whole number line range from 0 to 10. So it doesn't make sense to ask, well, what's the probability that my dog is going to jump 2.55555? We don't care that it's exact in that value. We care that it's in a range. So what I would rather ask is like, what's the probability that my dog has been training a bunch? And so I want to know the probability that my dog has been or has jumped in this range of 5 and 7.5, because that would guarantee a championship. And that's a question that we can answer. So, how you do that, I mean, this should make intuitive sense. Like, this is more, like, it ends up like a geometry question because all of these are equally likely. So, this distance is 2.5, and then our whole entire sample space is 10. So, it's 2.5 over 10. And that's kind of the same format. We have this whole sample space, this whole distance, and 2.5, so it's 1/4. Great, so that is a continuous random variable. It's a simple one because all of the intervals are equally likely, but it's a good baseline for us. Okay, so let's check our topics. Random variable. So we have the basics of random variables. That's fire. Okay, so now we're going to keep chugging, and we're going to talk about expectation of a random variable. So, I mean, the one word you should, or the few words that you should already, or that you just kind of have to think of as what this is an average, it's a mean, it's what you, the expected value. So, in any scenario in probability, you have, pretty much you have an experiment that you're doing. So let's go back to the basics and say our experiment is one die roll. Whatever. It's just a singular die roll that can be 1, 2, 3, 4, 5, 6. And so x equals the value of that roll as a random variable. So we're defining that random variable. So this is the notation for it. We want to know what is the expected value of this experiment. Like, if I were to bet $100 on what value that would happen, what would I bet on? What can I expect to be the average? And so that is the question that we get to answer with expectation. Okay, so there is a formula to calculate it. I would say it's not super helpful at first glance. You kind of have to understand what it means a little bit more. But let's write it down and break it down. So, okay, so this formula really combines pretty much everything we've talked about so far. This is the probability of an event. And then this is all the values in the range of this expected, or this random variable. So I didn't really talk about a range yet, but I've kind of been writing it down this entire time. And I was just kind of phrasing as what are all the possible outcomes. And so when you get into random variable land, you can think of it as here are all the possible outcomes. And let's say that this is the sum of two die rolls. So here are all the possible outcomes, but these look like 1, 1, 1, 2, etc. But there are only a few values that the random variable can take on. And that was 2, 3, on. And so these map to the final values of the random variable. Actually, that is maybe more accurate, right? Where it makes sense that this might not all the time be the same size as this. This is probably smaller. And like try this diagram out for maybe heads when number of heads when when flipping a few coins, and you'll see the pattern here. So the range refers to exactly this. These are all the values that the random variable can take on. So we want to sum through those, and they call this a weighted average. I mean that never really helps me, but it does like when you get the final value, but this formula does not seem like a weighted average to me when I just see it. So you're really just computing this. We can compute it quickly, but this is a speed run and I've got to go. So we're not computing this. And then, okay, so that is what expectation is. The answer here is 3.5 if you just do it out. And then, so you can define expectation, and it's really good to understand what it means because it's probably really important. I mean, it's definitely really important when you have complex algorithms and you want to maximize the expectation or whatever it is. But then there's also a lot of like algebra or sort of quirky things that you can do with expectation. You can do so we had the expectation of x was 3.5, but what's the expectation of x squared? And so that's a question that you can use what's called law of unconscious statistician. And instead of having x here, you would have x squared. And it's like, wow, is it really that simple? And it's like, yes. Great. So that is how you calculate that. And there's a bunch more rules that we just don't have time to go over. Sorry. But, okay. So there's expectation. And then expectation goes hand in hand with this thing called variance. So if we were to graph just a random variable, you've probably seen a distribution like this before, but we're going to get to it. So the expectation is exactly the average. So it's just the value in the middle. And then the variance is sort of like how far away from the average are the values. And that's really a picture that is good to keep in your mind. And the way to calculate variance is using the expectation. So you have to know how to calculate the expectation, then you can get the variance. Great. And then there's a thing called standard deviation, which equals the square root of the variance. Just because the units of variance are weird, and so people like standard deviation before, but you don't really have to worry about that. I just think in variance, and then when I need to convert to standard deviation, I just take the square root. But I think and do my calculations all the time in variance. Okay, so now we know random variables. We know what random variables are. And then we know some interesting ways about how to describe them, or some interesting properties of the random variable. We know how to calculate the average, or the thing right in the middle, and then we know how to calculate how far away the values are. And so those two things help us to understand what these famous called distributions are. And a distribution is just, in my mind, it's just a graph. It's a graph. Okay. So now we're in the land of famous random variables / distributions. Okay, so random variables are so common that some of them are super famous and have their own names. All of the examples that we've actually talked about so far have famous names. You just don't get to know that till the end of your probability course. So the first one is the uniform distribution. You can kind of think of it as like a function where you just put in the range of the values, and that's exactly what we were talking about before with the line from 0 to 10. And so when you define a random variable as a uniform, that's what it looks like, then you immediately know a bunch of things about it because it's just known by everybody. And so every random variable comes with a graph. So this graph looks like this because it's uniform, and these are the probabilities, right? Every interval has that probability, and that probability is in the graph. All right, speed run. So that's uniform, and then there's a bunch more. There's Bernoulli, which we've also kind of seen before. So Bernoulli takes in one parameter, which is the probability of a success. And that's all you need to know to then take on all of these interesting things. Like, you know that the expectation of a Bernoulli random variable is P. You know that the variance is P times 1 minus P. You know that automatically if you've defined X as a Bernoulli random variable. And Bernoulli is just like some dude's name. But what it means is that you have some experiment where the success happens with probability P. So flipping a coin, P, and you're looking for a heads or a tails, doesn't matter, but the probability would be half. Or if you're rolling a die and you need a 6, the probability is 1/6. So all of those could be modeled as a Bernoulli. Next, we have a binomial. And that, I'll get to these parameters later, is essentially when you connect, or when you have a bunch of Bernoullis in a sequence. So if you did a bunch of coin tosses and you wanted to know that how many heads that you've gotten, here we have 3 heads, right? But I want to know the probability that X equals 3. I want to know the probability that we got 2 heads, or the probability that we got 5 heads in a certain amount of tosses. So N corresponds in the number of tosses, and P corresponds to the probability of a success, in the same way that it corresponds to the probability of success of a Bernoulli. So this is a Bernoulli, this is a Bernoulli, this is a Bernoulli, this is a Bernoulli, bam, and so on. So we have N Bernoullis and Bernoulli's, and we're looking at how many successes did we get in those n tosses or n trials. And P doesn't have to be half in a coin flip. We can define it to be whatever we want. Okay. So those are the basics of probability. If I had some more time, I'll get into the other random variables, the famous random variables. Oh, also this is discrete, right? Because there can only be a certain amount of successes. So it looks like this, which is the discrete version of the normal distribution, which looks like that, which you've probably seen and you should get to in your studies because it's cool to actually know how that works, because so many things can be modeled with the normal distribution. I highly suggest, if you look up Chris Peach CS 109 from Stanford, I highly suggest these lectures that were posted on YouTube. This is what I watched, and I have never met this guy, Chris, but he is like an insane professor, just an absolute beast. So I highly recommend watching those if you want to learn more. So that was a speed run of probability. I have a final tomorrow that I'll be taking, and this was a way for me to formalize my understanding. So I'm sorry if that wasn't a great tutorial. Realistically, it was for me, not you, so stop being selfish. I hate to break it to you. All right, goodbye.